Okay, so this is the research presentation for the EE529 final. The topic that I chose was laser diodes. So in this presentation, I will go over the history of laser diodes. Then I'll talk about band structure of semiconductor laser, laser diode energy band diagram, recombination, laser diode state density, direct band gap and indirect band gap, optical feedback mechanism, heterostructure of a laser diode, applications of a laser diode, and then finally conclude with a quick conclusion. So starting with the history of laser diodes, the concept was first described by John von Neumann in 1953, and first semiconductor laser was actually designed in Japan in 1957 by Junichi Nishizawa. The first gallium arsenide laser diode was demonstrated as fully functional by Nick Holonyak in 1962. The first diode lasers were homojunction diodes. Homojunction diodes essentially mean that the material in the cladding layers used had the same band gap. The first heterojunction diode lasers were single heterostructure. So heterojunction diode means that they are formed from heterostructures, and heterostructures essentially mean that it consists of materials with different band gaps as compared to same band gaps in the homojunction diodes. Finally, the double heterostructure diodes were fully functional, and they were demonstrated to be working in 1970s. I think this was done by some Russian scientists back then. So starting with the band structure of a semiconductor laser. So crystals have discrete energy levels which split into energy bands, and each quantum state of an individual atom splits into certain energy bands. Essentially, there are two main bands that we look at, and they are the conduction and valence band. The energy difference between the conduction and the valence band is called the energy gap. For p-type material, the conduction band is partially filled. For the n-type material, valence bands are partially filled. There's also something called the Fermi level that measures the the Fermi level is essentially just a measure of the energy level that the electrons occupy. So for example, for the p-type materials, the Fermi level is close to the conduction band, and for the n-type material, it's close to the valence band. When two semiconductors with different band structures are combined together, then we obtain a heterojunction, which is basically a p-n junction. And a p-n junction is essentially what makes a diode work. That's essentially just a diode. So looking at the laser diode energy band diagrams, so I have two diagrams. So the one on the left is for the case when there is no bias voltage applied. So in that case, the Fermi level is at the same level, but they're essentially continuous. And in the case where a bias voltage is applied, there's actually a difference between the two Fermi levels. So applied voltage essentially causes recombination to take place, which is going to establish the diode current. And when the applied voltage is greater than the built-in voltage, the device is in what's called the active region. So for the second diagram, the device is in the active region. In this case, there are just more electrons injected into the common band than in the valence band. Okay, so moving on to recombination. Essentially, there are three kinds of transitions that are important for laser diodes, and those occur between the common band and valence band. So the three main things that we are going to focus on are the stimulated absorption, spontaneous emission, and stimulated emission. The relationship between those three is essentially that the rate of absorption is equal to the sum of rate of spontaneous emission plus the rate of stimulated emission. So stimulated absorption, basically in this case, a photon is coupled with an electron. And this causes the electron to decay to lower energy levels, and that causes the electron to release a photon. The photon is released at the same level at which the electron reduces to, basically. And the emitted photon has the same direction and phase as the incident photon. So for the case where stimulated absorption is dominant in a semiconductor, the main prerequisite for that is that the energy gap should be more than the difference between the energy of Fermi conduction band and the energy of Fermi valence band. And to basically separate the Fermi conduction and the Fermi valence bands, or Fermi valence levels, we just have to pump in energy in form of electrical current. And that's basically how this diode functions. Okay, moving on to laser diode state density. So we are interested in the state density because to study the optical properties of a laser diode, laser state densities are important. Essentially, state densities describe the number of available states per unit volume, per unit energy. So for the case on the left, that's for the case when the temperature is 0 K, and for the diagram on the right, that's when temperature is more than 0 K. So for the case where temperature is 0 K, the electrons and holes basically occupy the lowest levels in the conduction and the valence bands. And for the case where temperature is more than 0, there's enough thermal energy for the electrons to occupy higher states. Moving on to the next slide. So the direct band gap and indirect band gap. So the definition is that for direct band gap materials, electrons at the lowest conduction band level have the same momentum as the electrons at the highest valence band level. So it's essentially the peaks and the valleys are lined together. They are in a straight line, like right here. So they have the same momentum, but different energies. The reason why we're interested in this is because laser diodes are direct band gap materials. So that means that the electrons have the same momentum at the lowest conduction band and the highest valence band levels. The main benefit here is that being a direct band gap semiconductor maximizes the tendency of electrons and holes to combine by stimulated emission. So this increases the laser efficiency. So this is why, even though most semiconductors are indirect bandgap materials, laser diodes are direct bandgap, because this increases the efficiency. So in this picture right here, in order for the electron to move to the valence band or vice versa, it has to gain some momentum. So that's what this represents right here. So it needs more than just one particle, and that's what makes this process not so efficient. So moving on to optical feedback mechanism, high efficiency diodes require a resonator to amplify and feedback the input, which is a electromagnetic wave. So the resonator used is called the Fabry-Perot resonator. The way it's built is that there are essentially two mirrors which are placed perpendicular to the optical axis, and the mirrors are parallel to each other. And this resonator is used in heterostructure laser diodes, and what happens here is that the emitted photons reflect across the mirrors, and they are amplified using the process of stimulated emissions. So next, looking at the heterostructure of a laser diode. So here we are looking at aluminum gallium arsenide laser diode, and it has two heterojunctions. As you can see, the bandgap levels for the active material, which is gallium arsenide in the middle, is different than the two cladding layers surrounding it. So aluminum gallium arsenide laser diode consists of double heterojunctions formed by a lightly p-doped active region surrounded by higher bandgap P and N gallium aluminum arsenide cladding layers. So the main goal essentially here is to pump in electrons and holes in the active layer and then confine them to that region. So the potential for the electrons to travel to the active region is very low, so it just goes down there. But in order for it to cross the junction, the potential is set very high, so they're essentially stuck in this region, and that's the main goal because this allows for the amplification of light due to stimulated emission. Okay, moving on to the applications of laser diodes. So laser diodes are actually the most common type of lasers produced. Laser diodes are used in many different applications such as fiber optic communication, barcode readers, laser pointers, etc. So the reason why laser diodes are used in fiber optic communication systems is mostly because it has a large bandwidth, which means that it can carry a lot of information, and it's easy to transmit data using laser diodes over long distances. The way this really works is that we just add current directly to the laser diodes to modulate it. This is why laser diodes are the most common ones, because it's so easy to work with them. Okay, so the conclusion. So in this presentation, I started with crystals, how they have different discrete energy levels, and then they split into energy bands. Then talked about the PN heterojunctions. Then talked about the three important transitions for laser diodes: stimulated absorption, stimulated emission, stimulated okay, I think one is supposed to be stimulated emission and the other one is spontaneous emission. It's a typo here, but the relationship between those three were that the rate of stimulated absorption is equal to the rate of stimulated emission plus the rate of stimulated or spontaneous emission. And then I talked about laser diodes are direct bandgap material because that makes the device most efficient to work with. Laser diodes also use optical feedback to maintain high efficiency, and they use the Fabry period resonator, which basically has two mirrors which are parallel and they're perpendicular to the optical axis. Essentially, their goal is to amplify the electromagnetic wave input. And we talked about heterostructure diodes, which trap electron and holes in the active layer and use it to amplify light. Finally, in the application sections, we talked about how laser diodes are the most common type of diode and used in optical communications. So for this presentation, these were my sources. Essentially, I got all the diagrams that I used and all the explanations from these websites. So from sources 1 and 2, I got all the diagrams and the explanations, and source 3 was just for the application. So this concludes the presentation. Thank you.